Thank you for the introduction. My name is Akash, and I am a software architect lead at Intel. And I'm going to be talking about a couple of topics in this talk today. The first one being ZStandard performance and some of our experiences with benchmarking. We'll also give a preview on some hardware-based acceleration, which you'll see in the coming slides. So these are our presenters for today. Sarthak and Soji are also part of the presentation. I will also call out that this is a joint presentation between Intel and Amazon. So for our agenda, we have 3 topics, as I mentioned. So we have ZStandard based compression. Then we'll talk about QAT acceleration, which is hardware acceleration. Then we'll finally touch upon some of our learnings from benchmarking, OpenSearch. So before I move on, a couple of things I want to call out is why the problem of benchmarking. Why are we addressing this problem, right? So as you might have seen in previous presentations today was the storage, talk about storage, how data is just exponentially growing at every stage. So that pretty much makes it clear storage is going to become a factor as you consider storage costs. So compression naturally helps on that side. Second aspect to that is also background merges. So when we talk about background merges taking a lot of compute cycles, and thereby addressing that problem through compression techniques is very relevant. For the next portion of the slides, I want to pass it on to Sarthak, who will talk about indexing in OpenSearch and ZStandard.
Thank you, Akash. Hi, this is Sarthak. Looks like the slides are not the latest one. I had a joke prepared for you guys, but never mind. Okay. So yeah, before we talk about ZStandard compression and its effects, I would like to touch base a bit upon indexing in OpenSearch. So it is important to talk about indexing in OpenSearch because we want to set the context as to why we are here and why we are actually talking about ZStandard compression. Now, in OpenSearch, the way we manage our data is through OpenSearch indexes. Each of these indexes are made up of leucine indices. These leucine indices are called shards. Now, each of these shards has segments in them. These segments hold a subset of all the documents that are present in an index. These segments are also independently searchable for the segments and for the whole index. Now, I'm not sure if it's visible, but there is a sample NYC taxis document that is present on the screen. Now, each of these documents holds multiple fields. Fields are just made up of 3 parts. The first is name, the second is value, and the third is type. Now, let's check an example of one of the fields pickup location. The pickup location is the name of the field. The coordinates are actually the value, and the geopoint is the type of the field. Now, based on the type of a field, the leucine decides how it is going to process it, how it is going to store it in different data structures, like BKD inverted indices, and how it's actually going to behave. Now, the way users enter data or update their documents into leucine is via OpenSearch APIs. Most users prefer to use _bulk, and while we have other options like _create, _doc, _update, which perform a subset of operations that have that are present with bulk. But yeah, most users prefer to use _bulk. Whenever the document comes into leucine, it sees whether these fields are actually visible or whether these fields are known. And if these fields are not known, then the leucine updates them into segments as well as documents. Now, one such field type is actually stored fields. Now, what are stored fields? Stored fields are the fields which are actually stored quite literally, and they are stored in a non-inverted manner. The fields that are actually stored in an inverted manner are called indexed fields. A field can be both stored as well as indexed at the same time. Now, the great part about stored field is whenever there is a hit on a document, the fields that are actually returned in the response to a user are actually stored fields. This does not happen with the index fields currently. Now, with stored fields, since we are actually storing the data quite literally, these fields or these data is actually compressed before we are storing them. Now, we are compressing this data in a block of documents, not as per the document level compression, and that's done to achieve better compression ratios. Now, how are we actually managing the compression? So we use index.codec settings. It's a static index setting that determines the compression algorithm that we'll be using in the underlying process. And since it's a static setting, so basically users can either set it when they are creating an index, or they can update this setting by closing the index, updating the settings, and then opening the index. The important part about this setting is that it the segments that are already created with the previous codec or the original codec, they will remain as is. But the segments that are created now, the new segments that are created will actually use the new updated setting. Now, this is a very crucial setting because it impacts multiple flows in OpenSearch. You can think about indexing, re-indexing, merges, transforms, roll-ups, any of the core indexing flows that you can actually think of. In index.codec settings come into picture. Now, why is that? So we have an underscore source field in OpenSearch. Underscore source field is actually the JSON document that we have sent while we're ingesting the data. So whenever there is a search query, whenever there is a fetch query or in execution, source is the one that is actually returned. So source is always present and it is always compressed. So it determines how we are actually, so it's important how we are actually compressing the data to extract performance out of OpenSearch. Now, currently with OpenSearch, we have two compression options. One is the default one, second is the best compression one. The default compression codec, which uses an LG4 algorithm in the underlying in the background, it's known for its fast retrieval speeds. So if the user is not setting this setting, the index.codec in the when it is creating an index, the default is picked up. The best compression is actually the one that is known for high compression ratios, which basically means that your data is going to get compressed a lot, and it uses zlib algorithm in the background. Now, these are the two profiles that were taken while running a benchmark on NYC Taxi's dataset. Now, if we look closely, these 5-minute interval of CPU shows us like how roughly 10.5% of the CPU was going in the best compression or the zlib, and 4.26% was actually going in the LZ4 or the best speed or the default one that we have. So while this is working great for us, we wanted to look at other compression algorithms to see that whether we can improve this, whether we can extract more performance for OpenSearch. We talked about how best compression is known as spending a lot of time, and we just saw like around 10% of the CPU is going into compression itself, and the result is like we see around 34% of improvement in terms of store size when it compares to LZ4. So LZ4 is creating bigger indexes, and best compression is compressing them even more. Now we talked about how we were exploring multiple different algorithms, and ZStandard came to our mind. The reason is pretty simple. It's a more well-adopted, and it's an algorithm that actually is well-adopted, more popular, and it is known for providing a good balance of speed as well as storage. With ZStandard, we actually get the option for dictionary compression, and at the same time, we can tune the ZStandard algorithm in terms of what the users wants to do. If they want better compression, if they want better speed, they can easily tune that. With the introduction of ZStandard compression algorithm, we are introducing two more compression codecs, ZSTD and ZSTD nodec. With ZSTD, it uses a dictionary compression as a feature, so it compresses a little bit more, and at the same time, it maintains a good balance of compression ratio and speed. With ZSTD nodec, it excludes the feature of compression, dictionary compression, and at the same time, at the expense of slightly larger indices, it provides better read and write experience. Now we talked about how we can tune the trade-offs between storage and speed with ZStandard, and currently we do it with the help of compression levels. The compression level is again a static index setting that we're introducing for ZStandard codecs, and it's again either we can set it during the creation of an index, or we can update it later on by opening and closing an index. Currently, we are supporting 6 levels of compression, where 6 provides the highest compression ratio. So at level 6, if you're indexing, you are going to have smaller indices, smaller segments. With our benchmarking experiences, we have set the level as 3 as a default, because we found out that it provides a better storage as well as better balance between storage and speed, sorry. Now let's talk about performance with ZStandard a bit. Now, during our benchmarking experience with NYC Taxi's dataset, there were few of the trends that we observed, and I would like to point out a couple of them. So with indexing write latencies, we saw that LG4 was outperforming other compression codecs. But as we move on to the P90 latency, and if we see the throughput, we are actually seeing gains with ZStandard. So intuitively, if the P50 latency is better for LG4, the throughput should also be better. But that is not we were seeing. And I'm going to cover it a bit, like why was that the case. In terms of read, we saw that there were similar performances between across ZStandard and LG4. Although there were cases where we saw if the aggregations are based upon lookup of all the fields in a document, we did see LG4 was outperforming ZStandard. In terms of disk, the special part about ZStandard, it roughly provides the same compression ratio as the best compression, around 30 to 35%. And at the same time, we are getting better indexing throughput. Now, let's see the profiles for ZStandard. We can see that roughly 2% of the CPU is going into ZSTD node, and around 9% of the CPU is going for the ZSTD, which is expected because we are spending time into compressing more with the dictionary. And if we take reference from the previous slide where we talked about the profiles with LG4 and the best compression, we are seeing roughly 2% improvement in terms of the time and the CPU that is actually going into compression. Now, to summarize the store size comparison of all the codecs, we saw that roughly ZStandard and zlib are providing the similar compression ratios, where ZStandard is actually performing better in terms of storage. And with LG4, we are finding larger indices or larger store size. Now, we saw roughly 2% improvement in CPU, but how are we actually saying that we are getting 10, 13, 15% of gains in average indexing throughput? So what are we missing? The answer is merges. Now, these were the metrics that we captured during the runs with LG4 and ZStandard algorithm. Now, the important thing to understand is segments by nature are immutable. So whatever updates or any deletions that we're actually doing, the current segments will never change. Only the new segments will be created. The current segments will have the documents marked for deleted. So that's a separate thing. So constantly, the writer tries to merge smaller segments in order to perform the search efficiently. And at the same time, we want to reclaim the dead space as well. So since LG4 is creating larger indices, it is compressing a little bit less. There is a lot of merging activity that is going on behind the scenes. So I'm not sure if it's visible, but if you look closely, in the total merge size that we see during an LG4 run is around 103 GBs. Now, to put things in perspective, the store size for LG4 NYC taxis is around 36 GB, and we are doing 103 GB, 104 GB worth of merges. At the same time, with GSTD, we are doing around 71 GBs of merges. So, in a nutshell, we are roughly doing 32 GBs more worth of merges with LG4, and the effect of that is a lot of these background merges is taking away CPU cycle from active indexing. And when that happens, we are spending a lot more time in indexing that we need to. Now, this table draws a comparison about the phenomena that we are seeing. If we see the average latency, they're actually being hampered by these tail latency, which are getting affected by the merges. And we see that around 10% more, 10% improvement with the ZStandard noded codec, and the similar improvement that we see in the average throughput. In the middle column, if you can see the ratio of the worst 300 average latency, we see that roughly 40 to 50% of improvements in that. And that's solely because the merges are taking active CPU from indexing. Now, the graph on the left side, if you can, so this graph is basically the plot of the request and their corresponding response latencies. The graph has been plotted in the descending order of the response time. So the requests that are performing first have been plotted first. Now, on the right side of the graph, you see a P75 latency graph. We talked about how P50 latency was bad for LG4. Now, let's see for the P75 latency. ZSTD node has started to perform slightly better than LG4 for the P75 latency. And if we check for this phenomena with the P90 latency, we see that ZSTD node is performing quite better. And on the graph on the left side, we can see that how the slope for LG4, the black line, is actually so much that it actually start to affect the worst tail latency of the 500,000 requests, the worst 500,000 requests. Now, how are we able to capture all this data, and how was the benchmarking done? So we used a single data node cluster with a dedicated master. We were using a R5.2x large instance to perform indexing operations. At the client side, we were using OSB client, which was on a C6.5x large instance. And while we were sending the workload to our cluster, we were trying to keep the CPU at 90% so as to extract the maximum performance of the OpenSearch cluster. While we were doing these runs, we were monitoring a bunch of things. We were monitoring the throughputs, we were monitoring the latencies, we micro benchmark the compression latencies. So actually extract the accurate amount of data. We were checking different metrics like merge metrics, store size, the number of documents that were created, the number of documents that were updated. You're capturing the profiles for CPUs and allocation, as well as the time that was spending in CPU in compression. And we were looking out for errors if there are any 4x's or 5x's during the run. In this exercise, since ZStd we introduced it as a native library, we also had a learning where now as a part of benchmark, we are going to be tracking the memory of the instance as well, because some things are off even they are not being able to capture. So there is definitely an AI on that which we are going to follow up from the new native libraries that are going to come. Now I'll hand it over to Soji, who is going to talk about accelerated compression.
Hey guys, good afternoon. My name is Soji. I'm a software engineer at Intel, and I'm going to talk to you about hardware accelerated compression. So Sarthak mentioned, in great detail actually about ZStandard, the new ZStandard compression codec in OpenSearch. So hardware accelerated compression, as the name suggests, presents a new opportunity for even bigger performance. He also talked about the performance of ZStandard. So that's what I'm going to talk about today, how hardware accelerated compression can help us improve performance. So what is this hardware accelerated compression that I'm talking about? Well, it is Intel's Quick Assist Technology, or QAT. It's actually not new technology. It has existed for a while. It's been used in networking devices and exists in different form factors like a PCIe card. However, on the 4th generation Intel Xeon scalable processors, codenamed Sapphire Rapids, they're now available on board as crypto, and QAT is now available on board as an accelerator. So it's one of 4 accelerators that are available. These new Intel Xeon machines, the Sapphire Rapids, they are available on public clouds. On AWS, it will be the 7i series. And so, you should look out for that. So the QAT supports, as far as compression and encryption, for compression, QAT supports the deflate, LZ4, and ZStandard algorithms. The deflate algorithm is the algorithm used by zlib, which Sarthak talked about, and we're familiar with LZ4 and ZStandard, which Sarthak also talked about. So why even do all of this? The whole point is performance, right? We want to improve the performance, and how does this do it? So since QAT is an accelerator, by offloading compression to the accelerator, you're actually saving CPU cycles, and so that's useful there, right? Now you have CPU cycles to use for other things like merge, like we talked about. Also, it's the accelerator QAT is dedicated hardware, so it's actually faster, right? It does the compression a lot faster than you would do it on the core. So speed is another one, and you also get really good compression ratios. So you save on core, you save on your CPU, and you get the same or even better compression ratios. Plus, it's faster. That will improve the performance on OpenSearch. So, okay, I talked about the hardware. Now, let's talk a bit about the software. In OpenSearch, the main thing that we're going to talk about is the OpenSearch compression plugin. It currently does not exist. It's a work in progress. We are still building it. We're still developing it. But this is actually how we're going to be able to use QAT within OpenSearch, right? The plugin. So as you can imagine, while you're indexing or searching, using while you make compression and decompression requests, that will go to the compression plugin. And then now this is a software stack of what it uses underneath. QAT Java is it's a Java library. Excuse me, it's a Java library that's developed actually by engineers in my team. It's a generic Java library that just allows developers to use Quick Assist for compression and decompression. This also underneath calls on QAT zip, which is it's a low-level library that allows user space applications to also make calls to QAT for compression and decompression. This is a open source library, by the way. QAT zip and QAT Java, they're both open source and they're available on GitHub. QAT Java is available on Maven Central as well. And the links are included, so you can go take a look. And of course, you have your OS and the QAT hardware underneath. What are we looking for in the future? I just talked about the OpenSearch compression plugin, right? So the next thing that we need to do is to upstream that, get into the hands of OpenSearch developers. We would also like to add, this would include support for all deflate, deflate LZ4 and ZStandard algorithms. We also plan to publish performance data for on-prem as well as cloud instances, so you all know what to expect. And also, we look forward to having Sapphire Rapids available on all public clouds. So, in summary, QAT is this awesome piece of hardware that accelerates compression, and it's coming to a data center near you. So, look out for announcements on this. And now, Akash will talk about benchmarking experiences in OpenSearch.
Thank you, Soji. All right, so we had a great flurry of talks around benchmarking. We will have benchmarking, about ZStandard compression, then hardware compression. And the last part of this talk will focus on some of the benchmarking experiences that we have come across and share our learnings and findings. Just to give you some background on this, Intel, as you might know, is designed silicon, and we are most known for our products on the cloud, on the client machines. A little less known fact about Intel is also that we have very strong foundations in performance engineering, which means we are very adept at tuning, running, and getting performance, analyzing, and those are some of our strengths as well. What we want to provide at the end of the day is the best performance in both worlds. From the hardware, what can you do best to run an application or a workload like OpenSearch? And from a software side, what can you do to actually get that performance? Some motivations for why Intel is interested in this problem space, you might be wondering. As it is evident from the talks before in the morning, Eli also mentioned it, like this is a growing market. The amount of data that you're seeing is just going to grow. A second trend that we have observed is also customers wanting better performance per dollars, which means there is a theme of optimization in the industry, and OpenSearch is also a part of that same ecosystem. Lastly, Intel also believes in contributing and working on open source. As we all know, OpenSearch is a 100% open source product, and it has a very rich roadmap ahead of it. A last point that is not on the slide, but I will just mention it, is also the theme of new emerging hardware and how the data center of tomorrow will change. So as Soji mentioned earlier, the accelerators, they are going to start playing a bigger and bigger role, not just accelerators, but custom hardware, FPGAs, ASICs, all of those will be part of the ecosystem. And a lot of applications are starting to either experiment, prototype, try out how their services, their workloads run on them. On that last point, I think that is something we should all prepare for, is how can we leverage those new hardware changes in the best way possible. So on the benchmarking front, what do we do really, right? Like this slide pretty much touches upon what we want to do with benchmarking at Intel. We want to do, we measure run-to-run variance, and we show performance improvements. We use the public benchmarks as they are available today on OpenSearch. There's an OpenSearch benchmarking repo. We use that. We benchmark on the public clouds, AWS specifically, and we've also benchmarked our findings on on-premises machines. We use the out-of-the-box clusters configurations, and then gradually, as we see, as we baseline the performance, then we tune them for optimal needs. In the upcoming slides, you'll see some results that we have seen from just pure tuning. Next, in the benchmarking, what kind of things do we do in this benchmarking space? So in terms of workloads, we have indexing, which is writes and to some extent reads. and then search, which is more heavy on the reads. The type of experiments would include tuning, which means you have a baseline, and then how can you tune software parameters to eke the best performance on a given hardware. Scale out, meaning adding more and more nodes. How do you see performance changing? Scale up, where you can increase the size of your disks, network, compute, memory footprints. And lastly, new hardware generations. So as hardware evolves, performance characteristics change. Larger caches get introduced, more memory is added. So those things change the workload characteristics quite a bit. What we do with these experiments is we try to identify bottlenecks and root cause variants. So the next slide will just talk about a journey. Like we were identifying variants. We identified variants in a while benchmarking OpenSearch, and this slide will like kind of narrate our experience as we went through it. So the problem that we ran into was this was on the Amazon cloud. Where we were trying to benchmark OpenSearch. We saw a search for search workload specifically. We saw a variance of around 14 to 23%, which means running a search workload on Amazon instances, one time you would get a result that was like if you compare two results on the same hardware, they were in the 14 to 23% range variant. Now that's a problem. So what do we do about it? So first, we set a threshold, like what is acceptable in this regards. So for our purposes, we said if there's a 5% variance, let's keep it under that if we can. So a couple of things we tried from the cloud side. So when we talk about cloud infrastructure, what can we tune? So we tried to change availability zones. Did that have any impact? No, not really. The variance we saw was less than 5%, so it was not a factor in this. It was actually less than 1% if I recollect. Then we tried instance placement groups. This is another strategy that AWS shares. It's all publicly documented. If you try to change instance placement groups, you might see better performance. That did not contribute to the variance either. So then we thought maybe we are looking at the wrong problem set. Maybe we should look at something within the workload that's causing the variance. So then we pivoted to indexing and index-based learning. So what can we find about the workload that is actually causing the variance? So we took this effort that we were doing on the cloud and said, let's run it on a machine where there's no cloud-related factors. And what do we observe over there? So the next set of learnings that you will see are based on an on-prem environment where the cloud factors were taken away. So when we reboot a cluster, for example, what did we observe? A variance of 3%. Reboot does involve moving of the indexes around, so there is it's not going to be an exact match of what you had, but the variance really did not impact anything. Next thing we tried was in a multi-node in a lab environment. If we used a multi-node and then we copied indices around, we actually saw 11% variance, which is beyond our threshold. So we thought, well, this is something we can actually investigate and let's see what we can find out from it. And if we can bring this number below our threshold of 5. Then we tried reindexing. Did not help much. It brought it down a little bit, but we thought there's something else we should be doing. And finally, we arrived at snapshot restore after some research. And when we actually use snapshotting and restoring, like you snapshot to a remote store, and then you restore from that, then variance was actually below the threshold that we had, about 4.9%. So to summarize this slide, looking at it purely from a workload perspective, we were at 11%, and then from 11, we came down all the way to 5%. Now, did this solve the entire problem? It solved it partially. So the 11%, if you look at it from a total variance perspective, it's about half the workload size, half the variance size, sorry. So where we were at 14 to 23, half of it was due to indexes and the other half was due to infrastructure. Now, what could be those infrastructure problems? Noisy neighbors. We also used some of the preview SKUs. So the SKU we used was Sapphire Rapids, which was in preview at the time. So could those contribute to the variance? Possibly. It's an open question. So that was on the variance portion. Next, I want to just share some results that we have obtained from software tuning. So this is a documentation that we published about software tuning. Now you might ask, what is great? Like somebody identified tunings and they published a document. So this was actually a joint Amazon and Intel collaboration effort, and for OpenSearch specifically, where Intel actually identified the optimizations. We did that through the course of our benchmarking, the things I showed you earlier. We collaborated with the Amazon OpenSearch team, and we also collaborated with the OpenSearch content writers. And it was a pretty phenomenal collaboration where we were actually able to propose changes, get it accepted by the team, bring it up to the community, and eventually land it in a documentation that the whole community can leverage. This is also an example of some of the work that Intel does to make sure that everybody benefits from the work that we are doing. What came out of this as a result of this, on a hardware of Sapphire Rapids that is available as R7IZ, we saw about a 60% improvement. And what were those configs? We played around with Java heap sizes, the flush translog threshold size, the index buffer size, the index refresh interval. I mentioned the compression algorithm, but that was not tuned in this work. Details on all this is available in the link, so you feel free to use that. The next slide is talking about a scale-out experiment that we did. So basically, if you double the number of nodes at each stage, the expectation is that your performance will double. So we do see that with some of our Intel platforms, R7IZ again. R7 is the Sapphire Rapids Gen 4 Intel that my colleague showed in the earlier slides. That is available as an EC2 instance today. So you can see the performance is ranging from 1.85 to 2.1, which is roughly in line with the doubling at each stage as expected. This is a new hardware performance that we also measure. We call it gen over gen performance. R5 is a performance. R5 was an instance that was introduced about 4 years ago. It's the Cascade Lakes Skylake generation. R6 is the Ice Lake, which is the previous generation. R7 is the latest product in the Intel portfolio. So as you can see, gen over gen, there's significant gains coming out of just using a new hardware. For the previous generation, it's about 26 to 34%, and for the latest generation, you'll see about a 40 to 70% gains. This is no changes on your workload, just running it on a new hardware. So to summarize the work, if you want to take away some key learnings, if you want to remember this presentation later on and like what we talked about, ZStandard compression we talked about it provides a good balance between your storage and speed. It also gives you various options to tune the algorithm, so you can actually make more granular for your use case. Q80 is a new hardware, so keep an eye for that. It's going to definitely benefit compression, depending on the customer workload to varying degrees. We are quite optimistic about that. Benchmarking, one key learning was to use the latest hardware. A lot of performance gets left behind if you're not using it. On most clouds today, Amazon, Google, Microsoft, in the PRC clouds as well, the latest hardware is available. So if you have an opportunity, try to leverage that. Generic benchmarking is useful to some degree, but as a customer of OpenSearch, if you have a proxy workload, that might be better suited for measuring benchmarking performance. Lastly, tuning a cluster is necessary based on your scenario. It might be from a performance perspective, you can certainly gain a lot, both hardware and software perspective. Thank you. I think that was the last slide.